fine? Like just normal? Okay, like no need for the microphone. Fantastic. So right after the break, I'm going to talk about the compiler for GeneSys, and then how to let things off, talking about our software simulator and our verification. So just to introduce myself, my name is Christopher Priebe. I'm a PhD student in Javier Malazades' lab. My research interests are interplay of compilers, ML, and systems. If you're interested in checking out my very underdeveloped website, the QR code. Just before we get started, to get some acknowledgements out of the way, I would like to thank Dr. Sean Kinzer. He currently works at Qualcomm. He graduated, I guess, sort of about a year ago now. He's the primary author of the compiler that I'm going to present today. And he was also a great mentor at getting me introduced into the lab last year. And then I want to thank Rohan, who talked, Hanya, who will talk, and then Suresh, wherever he went. They did a lot of work with Sean on verifying the compiler for GeneSys. So I'm indebted to you all. So starting very high level, what is a compiler? I would say that it's some software that's going to convert a program written in a source representation and potentially with improvements, but still keeping the same function, give us some sort of output, likely an executable representation of whatever sort. Maybe we're going from a high-level language like Python down to like Python bytecode for the interpreter, or in the case of maybe like C compiler, going from C and then going straight to instructions that can be executed. And in terms of this project, why do we need this compiler? And the reason why we need a compiler here is, well, first of all, like Suresh had talked about before the break, GeneSys is programmable. Very specifically, the tandem processor has a lot of possibilities with the sort of primitive operations that are implemented. And so to enable us to have that flexibility down the line to support, to really leverage the whole goal with tandem processor to be able to support these new operations, we want to have a compiler that can take high-level representations of our algorithms and then turn that into the actual binary that we can execute on GeneSys. Secondly, GeneSys is highly parameterizable, which means we need a compiler that can actively target a moving target, essentially, because we can change the sizes of the memories, we can change the sizes of the compute units, we can even add new instructions, like that was mentioned previously. So we need a compiler so that we can keep a high-level interface even when we're dealing with a constantly changing target. So moving into the challenges with compiling for deep learning accelerators. Looking at this diagram here, right now there's like a multitude of, like a very rich ecosystem of various deep learning compiler stacks. NoTVM came up a couple times before the break. And right now, I would say, sort of in general, they do move through a unified interface, which is LLVM. Obviously, there are sort of like you can work and improve upon their backends to support your own devices, but nonetheless, in general, the general support is there for LLVM. And when we're targeting, ever expanding space of accelerators, no sort of abstraction exists here that enables us to go through that layer and then be able to target however many different domain-specific accelerators we want. So looking at the challenges that we've identified here for compiling to accelerators, I've listed 4 here, and I will go through these in detail, but just to quickly read them off: targeting diverse compute models, accounting for the software-controlled storage, controlling the explicit data movement, and then mapping actual operations to the various components in your architecture. So digging into these, when we're looking looking at a typical general purpose processor, usually we're going to be using some sort of fine-grained instructions on an ALU. However, on a domain-specific accelerator, for instance, like GeneSys, we can do an entire general matrix multiplication in just sort of one instruction. Obviously requiring supporting data access instructions and such, but nonetheless, like it's one operation for the entire gem. And this can be incredibly diverse, depending on what accelerator we're working with. And we don't know what that's going to be ahead of time, so we need to address that. So next, in terms of controlling on-chip storage, when we're talking about general purpose processors, we have this hardware managed memory hierarchy, and it makes things, everything's hidden behind the ISA with the CPU, and so we don't have to worry about the intricacies of this as a compiler, but with a domain-specific accelerator, we can have some sort of complex memory hierarchy, maybe with multiple different levels of scratch pads, where we need to keep track of the data that's in there ourselves and make sure that it can fit and that it's actually in the memories when we need it. Sort of in the same line, talking about data movement, once you load something into your register file, you just say add R1 with R2 and R3, and it's automatically going to move that data to the ALU and then put it in the destination register. When we're dealing with a domain-specific accelerator, we might need explicit instructions just to have that data available to the compute unit. And then finally, in a general-purpose processor, we're splitting everything up into these very fine-grained instructions. Obviously, I'm not referring to any sort of extensions, maybe like EBX or something, but just kind of in general, we have these very fine-grained operations that will split everything into, whereas with the domain-specific accelerator, we could have all sorts of different units on our architecture that might be better at doing one operation than another, and we need to be able to map our operations efficiently onto these components so that we can realize the full performance benefits of our architecture. So, to enable multi-acceleration, and here multi-acceleration means using various different domain-specific accelerators to achieve acceleration. We're going to address this with two separate points. One thing I just want to address here before I continue is that this entire tutorial is in the flavor of GeneSys, but our compiler does inherently support the ability to target various different architectures, not just GeneSys, and I'll delve into that a little bit later. As for the multi-acceleration itself, the first step on sort of the higher level side is using a fractalized representation that will represent the algorithms that we're trying to compile at many different granularities of computation. And then we're going to use an architectural abstraction on the lower end of things, coupled with a high-level programming interface that sort of is kind of like the kernels that many people work with for high-performance computing. And using this, we can achieve architecture-aware sort of scheduling. To move into the high-level portion first, I'll just give a quick overview of these, and then I'll talk about the compiler. So the high-level representation, we call this the FDFG, or fractalized data flow graph. So the figure here is, I guess, kind of like an arbitrary example. So it's just like a normal data flow graph where the vertices are the actual computations and the edges are the data movement between those computations. But here, every sort of top-level vertex has a sub-graph that is another like FDFG data flow graph that represents what that node's actual computation is. So, like for example, the darkest blue here is some operation, and then it is composed of these 4 operations that feed into one final operation, and then we can look even farther down and see that there's some more sub-operations. Then we get down finally like this lowest level of computation. It's just a ton of primitive operations like additions or hyperbolic tangent, etc.
So those are not tiles because they're very similar. The first level are not exactly the same, right?
Yeah, they don't have to be. Like maybe it's sort of a very ambiguous example. Yes.
The question is, how does these tiles play into a role here? Do you assume tiling is after this thing or before, or you subsume?
So
this?
sort of like tiling, as in like tiling the memory hierarchy.
Yes.
Yeah. So one, I guess this is sorry. Yeah, I should probably make an important distinction. So when I'm looking here at this high-level data flow graph, we're not considering any details about how things are actually executed. It's a very algorithmic representation.
So memory is
like
no buffers is virtual tensors.
This is like this is a very like high-level representation. You can think of it almost, and this is something that I'll even touch on a little later. It's sort of like mathematical formulas. Like if I say like a matrix multiplication is a summation over two tensors that you like iterate over, and here like there's no inherent specification over how we're actually iterating over the tensors. Like it's just saying, you know, the input is these two matrices and the output is the matrix multiplication. So it's a very high level specification.
Is this just curious? Is this fractalize means something?
So the fractalize is the idea that we can sort of keep zooming in. Zooming in as much. That's the theme.
Because there is fractal theory somehow, but I don't think it's related to.
Sure. Yeah, fractalize is just sort of the theming behind.
Fraction.
Yeah,
Fraction.
being able to sort of zoom in. Sure. So, like, maybe why do we need this in the first place, right? So when we're compiling some sort of model, we have whatever accelerators available to us to compile. So they could have various different compute capabilities. Like, you know, one accelerator, like GeneSys, has a dedicated systolic array on it, so then it has, like, it can do great matrix multiplication. Maybe there's another accelerator that is, like, incredibly good at, I don't know, average pooling or something. So we want to be able to represent our computations at the various granularities. So at the coarsest granularity, if we're just looking at the average pooling node, and one of our accelerators has the ability to just run that as a primitive operation, like just this average pool, then we can map it there. But if that's not the case, well, the tandem processor can do that with a couple of operations. So now we represent this at lower level, and we can map the lower level nodes onto our accelerator's compute capability. So this ability to zoom in and out and represent the computation at different granularities enables us to target the diverse compute models of various domain-specific accelerators. This is just a little example related to mobile robot trajectory. I don't think it's not like the example's not completely filled out, but it sort of gets the idea. Like the predict trajectory takes in what the current position of this robot is, and then gives out some position prediction. Then there's some gradient update based on that current prediction that we can give to some function that updates the internal model, and then gives us our output actual control signal to a robot, and also sends back the model again to do the trajectory prediction. So each of these are high-level sort of function operations, and then they're composed. The compute gradient is composed of some lower-level operations, and you know, if we're compiling to GeneSys, you know, maybe we can map an entire matrix vector multiplication on. But if that's not the case, then now this is it's expanded off into even more subnodes, and it keeps going down. So sort of re-illustrating the idea that depending on what we have downstream, we have the ability now to represent all these inherently. And so this is sort of kind of an example compilation in a scheme where it's sort of the same, whatever ambiguous representation. And depending on which accelerator we're targeting, we might have a different sort of grouping of these primitive vertices. So like in this, we have the ability to target, dangerous, the trap. Like we can map like maybe these higher level, like intermediate vertices, or in the case of whatever accelerator, maybe we have to just do the lowest level computation to be able to achieve the overall result. Are there any questions about the fractalized data flow graph high-level representation?
So like this selection, like optimization process is essentially you have this fractal, you kind of design the operators. Like so like over here, I mean, so the fractal essentially you have, if you look at like the lowest of the equivalent, will eventually have like these primitives.
Yeah.
And the initial graph will have some level of hierarchy.
Yeah.
And in the optimization process, you change the hierarchy such that the graphs are still equivalent at the summative level, but the way you will map the layers is going to be different. So is that what you do?
For like in terms of optimization?
It's like what would you do in that class? Like you just rearrange the nodes in like some dimension.
So I'm not sure if I'm understanding your question correctly. In terms of optimizations, like you have the ability to just look at some higher level, but you can also sort of during the optimization pass traverse down. Like I guess like thinking of like a visitor pattern almost, like you can sort of traverse down too, and then come back up, and you can control the level down that you want to go, for instance. Is that, I mean?
When so say you go down to a certain level, and then do you like merge these operations, like use these operations into say just one block? Over here, like you are kind of breaking the outer boxes and then reshuffling the boxes such that you get like basically driven.
I see, okay. So are you saying like how sort of this is constructed and achieved?
Yes.
Sure, yeah. So I would think that, so obviously the original program will have some level of, I mean, I guess depending on what representation you give, the original program might have some level of hierarchy built in. Like when you think about how you might program something anyways, like you're not going to repeat the primitive code for like a matrix multiplication every single place you call a function. So some of this stuff, it might already be embedded into the program, but then like I think ultimately you just need rules to do this rewriting top down. Like you need some sort of rules like, okay, I have to take this operation and I can break it down into these primitive operations. And that is sort of, I guess, achieved with a library of operations available implemented with primitives. So then
so like these rewrites, but essentially I mean these equivalent rewrites that are like you can have quite a few of them. So like do you rule this space like based on the aspect which you're targeting, or is it like you search the entire space and you see which one actually matches?
So I mean, I would say that like I would argue, at least reasonably, that you can sort of greedily look at the highest level first and then move down.
So you try to, when you take in the high level matches, you try to
yeah, sort of, but this is like a place where you might need heuristics and also like some sort of feedback mechanism, and that's like something an important like sort of overarching concept to consider. The idea that there's a lot of stuff with the entire frame, like the compiler framework, like you have some sort of there's like a set of parameters that define like how the compilation is done, like what the tiling splits are, like the loop order, like which like how much memory is used or whatever. So there's some set of parameters, and that like those parameters might apply here to like how the operations are mapped. And this is something that might need to be iterated over to actually achieve some sort of like optimal mapping.
These things are fine. Can you continue this?
No, I'm sorry. I feel like I'm not. Like we can talk afterwards. I'm not understanding your question exactly. Are there any other questions, or just good to go? Okay, fantastic. In terms of the lower level side of things, the architectural abstraction. So we use what we call an architecture covenant graph, which is a directed graph that represents the sort of architectural topology. And our compiler backend uses that to do sort of architecture or scheduling. So in terms of representing architectures, here is not actually GeneSys, but sort of a GeneSys adjacent accelerator high-level architecture design with various different components. It's got some memories, some interconnections, a couple compute units, and a little bit of additional controller or whatever modules. And when we're doing compilation, some of these things are necessary and some of them are not. For example, that controller logic that I was mentioning, like we don't care about what this finite state machine controller is doing when we're compiling, but in terms of like the memories, the interconnects, the compute units, these are the things that are important because this is the way that data is moving and actually being operated on, and that's what our programs do. So our architectural representation, this graph, the vertices are either memories or compute units, and then the edges are the interconnections, and these can be going in both directions as well. And so this sort of gives us this very high level sort of topology of our architecture that we can use to actually sort of schedule these high level algorithms across our architecture.
No control here, right? Control?
No, yes.
Okay, no control?
No, so those controllers, all that low level stuff like that, unless those components are like acted upon by the instructions like directly maybe. So at least like for GeneSys, like the instructions are, I mean, we have instructions that like we set those iterator tables up and then that moves stuff and then it moves stuff and then it has some compute and then it moves it back and then moves it back. So this is what we're trying to target with this architectural representation.
So we assume synchronous processor. Everything is driven by instructions. Let's continue.
Okay, it's like, so really, so each of this is just the topology, but we still need additional information about our architecture to actually like see the benefits of having a representation like this. So each of these, the different sort of components like the edges and the vertices can contain attributes that sort of parameterize them and give information. Like, for example, when we're talking about a compute unit, like just a node that's called something doesn't mean anything, but we can embed information about the actual operations that the compute unit can achieve into there so that the compiler has access to that and can use that information to do operation mapping. On-chip storage, sort of the same thing. We have information about the size of the memories, and then with interconnects, like for example, we can have information about the bandwidth, so we know how much data we can put over there. But this architectural representation isn't enough by itself because just the architectural representation doesn't give us a way to actually map how some operation would be executed to the architecture. It sort of is just the toolkit that we need to achieve that connection. So we also have a construct that we call codelets, and these are the things that give us the way to do this architecture-aware scheduling, which, by the way, is a manual scheduling thing with a little bit of parameter solving built in. But as you'll see, you have to do, at least right now, at least some of the manual work to define how things are executed. So codelets will make more sense probably with an example. So this is a ReLU codelet. I'm going to break it down piece by piece, but the codelets right now are implemented as a sort of Python embedded domain-specific language using the Python context managers. So we first open up like a context manager that defines like some codelet object that we're going to act upon, and we need to define different pieces of our computation for the compiler to use. So the first thing that we'll do, because we want like some operation, in this case we're defining how a ReLU would be executed on GeneSys. By the way, this is like the actual ReLU codelet for our architecture that the compiler uses. So For a ReLU that is dealing with like an image, we have 4 possible dimensions, and we'll define these dimensions, so let's see H and W, and associate these from our high-level representation, different, I guess, like indices of the shape. So for example, we would map the n, the batch size, to the first dimension of the first input, which is the data. And so once we have our sort of, I guess, sort of like placeholder value like variables for the dimension sizes, then we can actually define the operands that we're going to be working with in terms of those. So here we'll define one data operand x and then the output, and we'll define them in terms of their shape using those dimension placeholders from before. And then we'll iterate over those dimensions and do some actual transfers and computations. So there's these sort of like primitive operations built in to say like, okay, so how we're going to do the ReLU is we're going to transfer our data from DRAM to some sort of vector memory. Then we will do the actual ReLU on that data indexed at wherever we are in that loop, and then we'll put it in the output tensor at the same axis, and we're going to be targeting the SIMD, which is the tandem processor, so that gives the mapping to the compute unit there, and then finally transfer the output back from the vector memory back to the DRAM. The final sort of portion of this codelet, right here, this is just kind of a simple function call, but when we're doing compilation, for instance, we do sometimes and often actually need to set compilation constraints so that we have a valid compilation. For example, like we'll have constraints that will say like what a valid tiling will be. So, for instance, like a valid tiling has to fit on the vector memory, the tile, right? Like obviously it can be bigger than the vector memory. Another one that often comes up is when we're dealing with a reduction, like a matrix multiplication. We can't tile over the channel dimension without also doing like a load for that partial sum. So for instance, if we were to tile over the channel dimension, think that the channel, like the height and the width and the channel dimension goes out. If we were to tile the channel dimension, so we would split this into 2 segments and reduce over both of them, we would have to add those 2 together, right? And that defines like that's a separate sort of step. So for instance, if our codelet says we don't load the partial sum at all, we just do the reduction and then store it back, we would have to add a constraint like, okay, you can't tile the channel dimension. The constraints are very general, so this adds a level of like programmability to this interface. So you can define whatever compilation constraints you need to achieve your final goal. Yes?
These constraints which you mentioned, like SIMD and like reduction constraint. So like you have fixed number of constraints and like which you define, and then those are like then used in this overlay operation, right?
Yeah. So you define some constraints, yeah.
So you define these constraints as well as in the EDSM?
Yeah. So it's like it's sort of, it would be like writing like an assertion. Like I just said, this property has to be like less than some number or the size. Like for example, if I wanted to define a constraint saying, okay, the tile has to fit, I could say like, okay, well, the size of X needs to be less than, and then I look at the architecture covenant graph and say, I know how big this vector memory is because I have that information from the architecture covenant graph. I say like, it has to be less than like this, like the vector memory size, right? So we have those constraints. We have access to the attributes from the representation. That's like very important. So
like P1, P1, like DRAM and like SIMD, these are like the same terms which are presented like on which
yeah, I think that in terms of like between the presentations, like sometimes there's not a ton. Like sometimes the overlap is missed a little bit. Like so, it's like tandem, but then kind of just like terminology thing, but the SIMD is like the tandem processor, the vector unit.
So for every accelerator or like every architecture, you would have to rewrite these coordinates.
Yes, good question, yes. So going over just a quick overview of what the current compiler for GeneSys is right now. So right now we use ONNX as our input format. ONNX stands for Open Neural Network Exchange, if you're familiar. It's a high-level representation of a neural network as a computation graph. The various frameworks like TensorFlow, PyTorch, support exporting to ONNX, and so that's why we use it. It's highly interoperable between these frameworks. And so the front end of our compiler turns the ONNX model input into their high-level FDFG representation. And then we can do with the FDFG, we can do these high-level optimizations, like for instance, operator fusion, or maybe some algebraic rewrites, like code elimination or constant folding, constant propagation, etc. Once we have some sort of optimized high-level representation, then we'll have a sort of mapping stage where we take in those codelets and then we do the mapping from those high-level operations to their corresponding codelets, and then we'll get an output as a set of instantiated codelets. So important, like this is sort of a library, and then we have the set of codelets that are instantiated. And by instantiated, I mean the shape placeholders are like filled in now, because all the compile time information has now been filled in, and these are set. There's no ambiguities anymore, and we're ready to continue compilation. So moving on, then we'll do some sort of, I guess, like optimization / scheduling stuff with the architecture covenant graph as context for this. And this includes information like when we have the architecture covenant graph information, then we can do things like we can do the tiling now that we know how big the memories are and such. We can do memory allocation now that we have information about like DRAM and such, and more. So this is the point where we do these, like we apply these like scheduling primitives to actually give us these scheduled codelets that we can send off for final code generation. And moving to code generation, the architecture covenant graph, like one of the things that it sort of contains as an additional attribute is a set of templates that map like high-level codelet operations to sequences of instructions that we can actually run on our hardware. So we use these code templates, and these code templates are parameterizable, obviously. So there's fields that the compiler does, like like address calculation and such. It'll fill in there and generate the actual accelerator binaries. And additionally, if desired, we also can do golden output generation. That is in terms of it uses random data generated, and this can be used for additional verification and such. So this is the GeneSys compiler implementation. I will say, like I added a QR code here. This repository is private because it's access protected. So if you are interested, sort of the same way with getting access to the GeneSys architecture, on the main GeneSys GitHub repo, you would have to fill out the form that is would be right under the title, and we'll get back to you on that. But this exists in this GitHub repo. I was gonna do a quick sort of demo. I don't know how this is gonna work. There's a set of instructions on the actual GitHub page for the compiler that talks about the setup. It's a Python package, so it's relatively easy. Just like make a new virtual environment, download the package, like things you could install -d dot or whatever, and then now you have access to a couple of commands. The sort of primary method to compile is this compile GeneSys command. The -m flag is the model path to the ONNX file. I wanted to see if I can dump over. I wanted to quickly try to compile something on here. So, oh gosh. So I've got Netron here, and I just want to show like a ResNet model. So I'm gonna go over how the outputs of the compiler very quickly. So this is really hard to see, but if everyone is somewhat familiar with ResNet, like just a basic convolutional neural network with residual layers. This is gonna be so hard to see. Like if I
You can take the laptop and do that.
just take it with you to make it so it's not like impossible to use the mouse. Gosh. No, it's like the cables.
Oh, yeah.
Okay, very nice. Okay, I'm gonna run really fast. Okay. Can't touch anything. So I'll send my link. No, that's not. How do I zoom in on this?
Command first.
Maybe a little bit more. Okay, can we see this?
Yeah.
Okay, there we go. So I've already downloaded and set this up. It takes a little while to download like PyTorch and such. Anyways, type. So there's like a bunch of different. There's a couple different command line arguments that are available, and we're also like working on adding more of these. I'll just do. So I'm gonna, by the way, this I have this ResNet model here in this models directory. So I'm just gonna quickly do so I'll just quickly compile this and I'll deliver both so that we have any idea when it's done. It's just gonna, this should be done in like 15 seconds or so. Okay, sweet, even less. So now there's a new directory, this GeneSys compiler output, which is where the output of that is. And inside of there is the output of our compilation. So for this, I used like just a very basic default configuration of the hardware for a 16 by 16 systolic array. So that information is set by a JSON file that has a bunch of different parameters. And I've included a couple of like random like in that GeneSys configs that's right next to output. But right now I just use the default one. But this is like a place where when you're feeding in the architecture information, like you would do it through this configuration file. So inside of this compilation directory, the output is going to be a folder for every single layer that we compile. So I'm just going to look. I think that the convolution will probably be layer 0. So I did not. I don't think I entered. Okay, there we go. So inside of each directory is like the same couple files. You can actually see them all.
Do LL.
You can do it.
No, I need to. Okay, there we go. Okay, so there's 5 files in here. So the binary and decimal files, these are text files, like they're just like different numeric representations of the instructions. So like it's just this is not a binary file, it's just a textual representation, but this is what I believe this is what our runtime ingests, yeah. So those 2 files, in terms of more interesting information, so that operations, the 4th one, operations_idx.txt, this gives sort of like a pseudocode-esque representation of the codelet, except with the actual the parameters, like the shapes filled in, and the tiling filled in. So I'll just print this out. So So like for convolution, right, we have all these, there's 2 levels of loops, and it has different information, like, so this would be like how many things we're looping over, like it's got the stride for all of these, and then at the lowest level, at least on our systolic array, we have the PE array, matrix multiplication. So this is sort of a debugging feature. And then finally, the last file that we have is this is the assembly sort of mnemonics for all the instructions. So this is sort of related to what Suresh was showing earlier, but this is where you can actually like debug different values and such with the instruction generation. So that's the this is the those are the files that are outputted, and that's everything that you would need to do. Everything that you would need to do software simulation, or actually run using the runtime from the compiler. Okay, cool. So there were some compilation flags there that I had shown. Some example compilation parameters, like in the actual code list themselves, we can modify various stuff, including like the loop order. The tiling is automatically found by the compiler using the constraints, but you could also, for instance, add a manual tiling configuration if you spend a bunch of time like maybe trying every possible one and then found your best option. You can manually put that in. Additionally, we support operator fusion, like Suresh said, using this sort of heuristic that we want to attach every single systolic array operation with a series of tandem operations. So these are, if you're using GeneSys like for a research purpose, for instance, and you want to do like sweeps and sensitivity analysis on these different parameters, like the compiler supports the ability to toggle these different things. In terms of new operations, if you want to have, like, if you want to compile some different operation, like, I don't know, for instance, like if you want to do maybe a discrete Fourier transform, right? That's not an operation that's currently implemented in our like library of codelets. But if you wanted to have that operation, all you would need to do, like, I don't think it's supported by Onyx or anything, but you would just need to implement a new codelet that defines how that operation is actually executed in terms of the primitive operations that are available on like the tandem processor or the systolic array, and then you would automatically have support for compiling that. Like I mentioned earlier, our compiler is not just for GeneSys itself. Like, we have the ability to support other architectures too. Like, for instance, this backend work is all from a paper that's available on arXiv. I mentioned it earlier. And for the evaluation there, like the original author Sean, he actually implemented a backend for Hexagon, which is a Qualcomm digital signal processing chip. And so if you wanted to compile to a new target architecture, you would first need to implement the architecture covenant graph and then implement a list of like a library sort of codelets there. But all in all, like, the implementing the architecture covenant graph part is definitely not like trivial, but it's all, the idea is that our compiler is here as an ease of use thing. Like, it enables you to have the capability to target other architectures if you want to go through a small amount of development effort to actually make the instruction templates, like get the architecture covenant graph and implement the stuff in code. So this is a good like stopping point. Are there any questions here before yeah, what's up?
So can you talk a little bit more about like fusing the operations together? How does the compiler choose which operations to fuse? And for a fused operation, do I need a codelet only for that fused operation?
Yeah, good question. Very good question. Okay, yes. First of all, first to the first point, like Suresh mentioned, so there is probably more like possibilities on how we can do like efficient operator fusion for GeneSys. The one that like we use right now is that because of the way that like, the software pipelining works, like we want to have the tandem execution where we're doing some sort of operation on the systolic array and then feeding like this tile down to tandem to do that and storing back. So right now our fusion is we're looking for either like a matrix multiplication or convolution that's done on the systolic array. And then we're then sort of greedily looking for some sequence of operations that will be done on the tandem processor. And then we'll fuse those all together into one codelet, because the way that the execution of, the way that everything's kind of laid out, like those layers, like there's different like blocks of instructions. So each layer in those output files I showed is like one sort of like block. And so we try to fuse that everything into one block. So that's at least how it's just the only way that it's done right now. As for the second one, yes, you would need a codelet for the fuse, like for each sort of fuse. That's definitely an area of improvement to make that more automatic. But right now, yes, you would need a codelet for that specific fusion example. Yes?
Yeah, from the initial presentation by your professor, I got the impression that this compiler is automatically generated. Is that the long-term plan? Or because given all this nice abstraction, architecture, graph, codelets, since the next step is to auto-generate
So
the compiler.
I think Chris will talk. We'll talk about the
Yeah, so your question was automatic generation of the...
No, entire compiler to be generated. Based on the architecture, description of your processor, on particular processor type, and your machine models, can you auto-generate the compiler?
auto-generate.
Yeah, like, what do you mean by auto-generated?
Generate code for the compiler, C code, C++ code, so that compiler, all these passes are
Okay,
generated.
wait,
So, just to be clear, Synopsys does this for the vector processor. Here, in addition to vector processor, we have matrix multiplication. I'm just curious how much it will take, or it's too much for us.
No, so what I think like is one important thing to note is that if we think about like the compiler as like a high level function that takes as something as an input and something as output, our compiler takes as input the architecture covenant graph and the codelets and outputs code versus us generating a new compiler for an architecture. Does that distinction
This is
make
what I'm
sense?
asking. This one.
Yes, so that there's the distinction there. So we don't.
For example, Synopsys, how to generate a new compiler. Given the machine description, you generate a new compiler automatically.
So we don't generate because our compiler is.
Specifically for GeneSys architecture.
So the goal is for our compiler to be general enough that that we can plug in the architecture covenant graph and achieve the code generation.
Okay.
That's the goal, right? So
good.
that's like instead of generating, does that at least like answer your question sort of? Okay.
Thank you.
Any other questions? Okay, cool. I'm running out of time here, so I'm going to quickly race through a little bit. So, as I don't know if anyone listens to any of Hadi's talks, but I've talked a lot about compiling like Onyx. We're dealing with compiling deep learning models because GeneSys is a deep learning accelerator. But as like mentioned, the tandem processor, right? So, like AI applications are not necessarily just deep learning. They have potentially many other constituent algorithms. This example here on the bottom is like not self-driving cars, but also like sort of the same wavelength where we need a lot of signal processing stuff in the beginning, and we might need some additional algorithms that are not deep learning at the end as well. So we need to look beyond just being able to support various operations in neural networks and move towards these cross-domain applications. So the way things like might be right now is that, you know, if we're dealing with a different like domain, like robotics or whatever, or digital signal processing, we might have like a domain-specific accelerator that's very good at just that, and it'll come with some sort of software stack that you can use to compile to it. But then we're having to move through like all these different software stacks and like orchestrate everything. And so our goal here is, well, if we can, we've already kind of like with this presentation, I've already discussed sort of this bottom part, like going from our compiler to like various different domain-specific accelerators. Like, what if we can take the top part as well and do everything just through this one interface? So here is where we introduce a sort of like cross-domain programming language. And the sort of common theme across all of these different domains is that they're really in the language of math, right? So, for instance, like a discrete Fourier transform, it's math, like model predictive control. These are just, they all kind of boil down to these mathematical equations. So, with the project that we're currently working on right now, I think Hadi called it, mentioned at 5 at the beginning. The goal is to sort of unify what I had been talking about earlier, presentation with this this multi-granular data flow graph, our multi-target backend, and combine that with some sort of interface to do this cross-domain programming. And so now we have a way to do, we have so many different algorithmic domains. We can combine this through a compiler, one unified interface, and compile to many different accelerators. And sort of what we're looking for here is like we want to be able to represent these different applications. We want to be able to code in a familiar language. And at least with this project, we're looking to do things very open with the community. So in terms of representing something, right, like this is sort of this model predictive control cost function. It's a couple of summations, and I can very naturally represent this with when we use these sort of index variables. These sort of index variables that describe like a range for a loop, something very common like polyhedral compilation, right? And so the mapping from here, like we use these index variables, and then we get a notation that's very similar to the original math. So we have summation, and then we do some sort of multiplication and subtraction. So here we have some sort of built-in like sum reduction function, and we're doing it over this I index or whatever, and then we access our tensors. So the subscripts, now we're just doing index access with our operations. And so here we're getting sort of a correspondence between, like, we can code in this language of math with our language. So I've given sort of a little example, a snippet, talking like with a sigmoid function, and this would be a forward pass for like a very basic neural network, like just one layer, like matrix multiplication activation function. So we have these type qualifiers that really explicitly control how data can be accessed. So like an input, for instance, is read only. Can't write to it. Vice versa for an output, that's write only. Like I was saying earlier, we have the ability to code these sort of mathematical foundations. Our language has calls to different subroutines. And the indices, probably the most important thing is these indices do not explicitly represent, they do not explicitly define the parallelism. So what I mean by that is, if we write like some code to loop over an array, like if you write that in C, even though the compiler might be able to move that loop order around, you are defining a loop order there. And if you did tiling, for instance, like you would define that tiling in those loops. But here, this doesn't say anything about how we're doing this computation. It's sort of coming back to that question earlier about like high-level representation. This is a very high-level representation. We don't say anything about how we're doing the actual computation. We're only saying what the computation is at sort of this like input-output level, this sort of input-output perspective. And I only have a couple more slides here. I promise I'm almost done. The workflow is very similar to the compiler from before. So kind of on this other side, like, you know, we're going to be going through that multi-granular FDFG, just because now, like, we want that ability to have multi-acceleration. So we want to be able to target different accelerators. So we're going to have that because of the reasons that I discussed earlier. But in terms of the front end, like we're working with this new language that we've been developing, the snippets that I gave from before. We also, not implemented yet, but we intend to have like, the ability to take as an input like a PyTorch model. And this sort of part here, like this is the short roadmap, but ultimately like it's just the front end to an intermediate representation. We would love to be able to expand this through open source development to like as many different possible input representations as possible, so we can target as many domains as possible. After we kind of move through our intermediate representation, now we need to go to the operation scheduling. So this original codelet backend is what I had kind of just discussed, but Another thing we want to support is the ability to actually do C and C++ generation, because, like for instance, maybe not all of your code can actually be run on an accelerator. I know like the affine accesses came up a little bit, right? Like GeneSys only supports the strided access. Like if we have some code that doesn't do that, and it has like the indexes squared for some reason, then we might need to be able to offload some of our computation to a general purpose processor, just because we're dealing with domain-specific accelerators. Inherently, we might not be able to cover everything. And so, as a final slide, this project is like the GeneSys stuff is been worked on and verified, and that stuff's ready to use. This actual Phi stuff is, I mean, in the last couple months here, this stuff is really budding, and this is our current, actually, at least my actively working project. We have a read the docs page where we have a sort of design blog where we meet, discuss some stuff, and we put it up to our design blog like right after we meet. And additionally, we're like an introduction post, we discuss our design decisions there. The point of this design blog is we're documenting our process to be available to anybody that wants to work with us. So if you are interested in giving any feedback, we're very open to this stuff, and we would love for people to come, look at what we're doing, give us feedback. If there's some feature that you don't feel is available to you in any sort of tool chain that you are using right now, these are the things we would want to know, because we want to be able to support as much as possible. So with that, I'm done. Are there any final questions for me? Sounds good. Okay. Well, thank you all, Han Yang. I leave it to you.